In this video, I want to go over a few examples on how to represent both pure states and mixed states in the Bloch ball. But let's first go over a recap of what we discussed in the last video. So the first thing we did was a refresher on the Bloch sphere, and we derived a state vector equation for a 1-qubit state as a function of the angles theta, phi, and gamma, so we can represent any pure state in the Bloch sphere. Next, we derived the density matrix representation for this pure state by just simply taking the outer product of the ket of psi with the bra of psi, and arrived at this expression after using some trigonometric identities. And what we notice here is that this expression no longer depends on gamma, so this global phase cancels out when we take this outer product, but it still depends on the angles theta and phi. Now, after that, we multiply components from this expression by this radius r, which was perfectly fine because for a pure state, r is equal to 1. After that, we looked at the elements of this matrix and replaced these polar coordinates into Cartesian coordinates and arrived at this new density matrix that depends on x, y, and z. And then we said that for pure states, this still has to follow the condition that this radius r must be equal to 1. But if now we allow r to take values between 0 and 1, then rho represents not only pure states, but it can also be used to express mixed states. And lastly, we manipulated this matrix so we could express it in terms of the Pauli matrices x, y, and z and the identity matrix I, and then arrange it in such a way that we can represent our x, y, z coordinates as a vector known as the Bloch vector, which represents the state inside the Bloch sphere. So now let's take a look at a few examples of how this works. And we'll start with some pure states. So here I've written down the expression for a state vector for a pure state as a function of the angles theta and phi. And here we have the density matrix as a function of the coordinates x, y, and z. So let's start with a very simple example. Let's start with just the state 0. So we know that if we look at the expression for the state vector, in order for us to get state 0, this cosine of theta must be equal to 1. So that means that theta must be equal to 0. Now, if now we replace that theta here on the sine of theta over 2, then this term will be equal to 0. Now, in the Bloch vector, we know that the angle theta is the angle between our state and the z-axis. So that would mean that our state vector is pointing in the plus z direction. But now, let's take a look at the density matrix for this state, right? So we know that the density matrix for the state 0 is given by 1, 0, 0, 0. So if now we take a look back at the expression for a general density matrix here, well, what are the values that x, y, and z must take so that we can get the density matrix for state 0? Well, if we look at this, the off-diagonal terms are 0, and that immediately tells us that x and y must be 0, right? So let's write that down. So x and y must be equal to 0. And then if we look at the diagonal terms, well, we see that we have a 1 in this first element here. That means that z must be equal to 1, so that when we multiply by this 1/2 and add up 1 plus 1, we get an element of 1 here on the top left corner. Now, if z is equal to 1, then this 1 minus 1 is going to give us 0. So that gives us the correct density matrix. So that means that z must be equal to 1. And in Cartesian coordinates, that corresponds to this vector we had drawn here when we used the state vector representation. So that means that by using the Bloch vector, where we have the components x, y, and z, we have arrived at the same visual representation inside the Bloch sphere. Now let's take a look at the next example. So we have the state 1 over root 2 0 plus I over root 2 1, and this corresponds to the state right, or the state R, right? And we know that in order to get this state using, let's go back to this state vector representation here. So in order to get this 1 over root 2 here, that means that this term of cosine of theta over 2 must be equal to 1 over root 2, and that happens for a theta equal to pi over 2, so that the cosine of pi over 4 gives us the 1 over root 2. And same here, if we replace sine of pi over 2, or pi over 4, that also gives us 1 over root 2. But we have this I component here. Well, that is given by this angle of phi, and we know that e to the I phi, for it to be equal to I, phi must be equal to pi over 2. So here in this case we need theta equal to pi over 2, and we need phi equal to pi over 2. And in the Bloch sphere, well, if theta is equal to pi over 2, that means we will have a vector here in the x-axis, right? This is theta equal pi over 2. And then if phi is equal to pi over 2, that will mean we have the state vector here on the y-axis, which corresponds to the state right. Now let's take a look at the density matrix for this state, right? So if we take the density matrix for the state right, we know that this is equal to 1/2, and we've done this before. You can double check that this is the correct answer. Is 1i minus I 1. So then what are the values that x, y, and z must take to give us this density matrix? Well, if we go up here, to get a 1 in the diagonal terms, well, the z must be equal to 0, right? And the off-diagonal terms are minus I on the top right corner and I in the bottom left corner. So that means that x must be equal to 0 and y must be equal to 1. Right, so if we write this down here, we now have that x and z must be equal to 0 and y must be equal to 1, which, you know, by looking again at our Bloch vector, which has components x, y, z, that corresponds to a unit vector along the y-axis, which is the same that we had obtained using the state vector representation with the angles of theta and phi. All right, well, now let's take a look at this final example where now we don't have a pure state anymore, but we have a maximally mixed state of 0, 0, and 1, 1 with equal probability of occurrence of 1/2. So in this case, we're not going to look at the state vector representation, but just at the density matrix, right? If we write it in matrix form, that is 1/2 with diagonals of 1s and of diagonals of 0. So what are the values that x, y, and z must take to give us this matrix? Well, in this case, in order to get 1s in the diagonal terms, well, z must be equal to 0. And to get 0s in the off-diagonal terms, well, x, y must be equal to 0. So that means that all three x, y, and z must be equal to 0, right? So x, y, z, all three equal to 0, which is a vector of length 0. So we usually represent that just as a point in the center of the Bloch sphere. So for a maximally mixed state with equal probability of occurrence, our vector has no length and it's just a point in the center of the sphere. Now, this brings about an interesting question, and is, well, then that seems to indicate that if we have something in between a pure state as a vector of length 1 and a maximally mixed state as a vector of length 0, well, anything with off-diagonal terms in between them must be a vector of length that is in between 0 and 1, right? So let's look at a last example where, let's say now we have a density matrix of the form 1/2 of 1 I over 2 minus I over 2 and 1. Well, to generate this matrix, our components z and x must be equal to 0, and the component y has to be equal to 1/2. And that will correspond to a block vector along the y-axis of length 1/2. So to wrap up this video, let's take a look at this application I created that allows us to visualize any block vector inside the block ball for different values of x, y, and z, and it also gives us the corresponding density matrix. So let's look at the two examples we had before, where we had a state vector for our state r, which corresponds to a vector in the plus y direction, and we said, well, if we now start decreasing the value of this y component, the off-diagonal terms are going to start decreasing, and we're going to see that vector go down. And then if we bring it all the way down to 0, which gives us a maximally mixed state, then we just have a point right at the center of the sphere, right? And anything in between just decreases the length of that vector. And this way we can represent any possible mixed state inside the block ball. So I hope these examples were helpful to get a better understanding on how to work with this representation.